Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to explore the strong induction principle, the weak induction principle, and the least number principle. And thank you very much to Nagamani who suggested we look at this topic. It's always great when we get suggestions from viewers. So this is the induction is something you'll come across at A level, but I came across the least number principle and the strong induction principle when I was doing a master's degree in philosophy of mathematics and logic. So some of these topics are a bit more advanced. It's basically degree level or master's level stuff, although people who are earlier on in their studies would also be able to follow this. The logic, logically, you can still follow it. And it's quite interesting. So the idea is to show these three principles are all logically equivalent, but let's explain them all first. So the principle of weak induction says this. If P is a proposition on N, the natural numbers, N is the natural numbers. If P is a proposition, if we know P is true of 1, and we know that if it's true for N, then it's true for N plus 1, then it must be true for all of the naturals. So the point is this, it's a bit like dominoes, which is, if you push the first domino, and you know that every domino hits the next domino, then all the dominoes are going over. So that's the weak principle of induction, which should be reasonably familiar. The next one is slightly different, which is the strong principle of induction, which says that if P is a proposition on the naturals, then if it's true that the truth of P for all R less than N implies the truth of P for N, then we know that Pn is true for all natural numbers. So let's just talk about that a bit. So let's say if we know that the truth of P for 1, 2, 3, 4, 5 tells us it's true for 6, and the truth for 1, 2, 3, 4, 5, 6 tells us it's true for 7, and the truth for 1, 2, 3, 4, 5, 6, 7 tells us it's true for 8, then we know it's true for all. By the way, we get the truth of it, the truth for 1 for free because it's vacuously true, because there are no natural numbers less than 1. So P1 is sort of vacuously true under this system. The final one is the least number principle, which is perhaps the easiest to understand, which is if S is any subset of N, then S has a least member. This feels probably quite natural intuitively. Of course, it's not true for the integers, so because you've got the negative integers. So there's lots of sets of integers that do not have a least member, although some sets do, particularly subsets of the naturals. But there are lots of subsets of the integers that go off to minus infinity. It's also not true of the reals. For instance, if you take all the real numbers greater than 1, not including 1, then that has no least member, because you can get really, really close to 1, but you never touch it. So, but this is absolutely true of the natural numbers. And what we're going to show is all these three things are equivalent, because the weak principle of induction implies a strong principle, which then implies the least number principle, which then implies the weak principle of induction, so we go round the circle. It's also worth just mentioning that the two induction principles are sort of talking about propositions, whereas the least number principle is talking about sets, and they may feel a bit different, but they're not so different, because actually every proposition has an associated set. That is the set of elements that make it true. And every set has an associated proposition. That is the proposition that a given element is in the set. So they're more similar than perhaps they might look. So let's start by assuming the weak principle of induction and setting out to prove the strong principle. So let's assume that we have, as in the strong principle, we have that if we know P is true for all R less than N, then we know that P is true for N. If we're given that, then what we do is we define Qn to be the statement that P is true for all R less than N. And from the above, what that tells us is that for all N, Qn implies Pn. That's kind of what this statement at the top is. So Qn implies Pn, but then if we infer Pn from Qn, that tells us Qn plus 1. Because Qn plus 1 is the idea that P is true for all r less than n plus 1, which is given to us from a combination of Qn and Pn together. So for all n, Qn implies Qn plus 1. Vacuously, we already have Q1, as we've said before, because there are no natural numbers less than 1. And so this gives us all we need to apply the weak principle of induction, which then tells us for all n q of n, which of course gives us for all n p of n. So given the weak principle, we've proved the strong principle. Now let's start with the strong principle. So let S be a set with no least member, which would contradict the least number principle. We need to show that S is empty. So we're going to define P as being the property of not being in S. Now, if all of the numbers less than n are not in S, then there's no way that n can be in S, because then it would be the least member of S, and we've said that S does not have a least member. So what we've got here is we can use the strong principle of induction on P, because we know that the truth of P for all of the members below n gives us a truth of P for n. So hence, all integers satisfy P. All integers are not in S, therefore S is empty. And we've proved the least number principle. We've proved that the only sets with no least members are the empty ones. Finally, we're going to use the least number principle to prove the weak principle of induction, and this is actually the one I enjoy most. I mean, they're all pretty, but this is really pretty. So let's assume that we have P of 1, so we know P is true for 1, and we know for all n, P of n implies P of n plus 1, and now we're going to employ the least number principle to show that P is true for all n. So let S be the set of numbers for which P is not true. We need to show that S is empty, and then that will show us P is true for all natural numbers. So if S were non-empty, it would have a least member, and it would be L. L cannot be 1, because we've shown that P of 1 is true, and L is in S, and S is the set of numbers for which P is not true. So L cannot be 1. Also, L minus 1 cannot be in S, because L is the least member of S. So L minus 1 cannot be in S. So PL minus 1 is true, because L minus 1 is not an S. And so by the induction hypothesis, PL is true. And this is a contradiction, because we thought that L was in S, which is the set of elements for which P is not true. So this contradiction shows us that S cannot have a least member, which means that S must have been empty, which means that P must be true for all n, and we've established the weak principle of induction. I hope you enjoyed that. I enjoyed that. If you'd like to see more, then please hit the notification bell and hit subscribe. If you'd enjoyed this, then please hit the like button to show you've liked the video. I'm a bit tired because it's 20 to 1 in the morning, but I just had to do this. I'd love to hear your ideas, more of your ideas, and I hope you enjoy your mathematics.